get back and wrap up stability analysis. We will look at the von Neumann. I'm basically barely going to, I'm going to do some examples. Von Neumann. Linear. Stability analysis. And let me mention to you the following. I went back to my notes, and you should look. I like very much discussing that Randy Levesque, as I mentioned already. I like very much his books. I actually had been the pleasure of meeting him personally sometimes, even though there's been a long time since I haven't seen Randy. So Randy Levesque has this many nice books, and I like very much this book here. Let me abbreviate the title because it's long. Finite different methods for ordinary and partial differential equations. It's a book by Siam. So it's usually Siam books are excellent and cheap. 2007. And for what we are looking at, I would recommend, it's a nice reading of chapter in his book. There are some informal notes of his, things get a little reshuffled. And his book, I think it's chapter 9. Yeah, chapter 9. This first part here, I don't need anymore. So it's chapter 9. And let me make some comments on, on what I sort of refresh my memory looking at the book. Because as I said, my notes I pick up from books here and there, many very nice authors. Trefethen is another one that writes very well. And at one point he had, I don't know if he still has, sort of some informal notes on his webpage too. Okay? And there's Randy Levesque, Strick Verda. So these are books which I use here and there. I mix. And sometimes I forget to put notes on my notes so that I remember where I got the information. So as I said, I have to organize things, further organize. So in this chapter where he starts talking about diffusion equations, but then at some point he talks about advection and other things like that, he will talk, let me sort of, I made a few notes for me to remember. So at one point he will talk about truncation errors, and he will comment. So what are our Randy's comments? So he'll comment about mol. Do you remember what mol means? Method of lines, right? And he will contrast method of lines. So he will talk about mol. Let me put it like this. He'll talk, right? He writes, but talk about mol and absolute stability. If I'm talking about absolute stability, I'm basically talking about ODEs, right? So it's quite nice that he talks about method of lines discretizations and absolute stability. And then he'll talk about convergence. And then with this, he talks in particular the following. There's a section, which in the book is section 9.1, which is called, which I think is very good to read, having in mind our cars. So he does a bit of a discussion between PDEs versus ODE stability. So when we looked at PDE, so he mentions about what's called also the Lax Richtmeier. I always forget the T. the Lax-Richtmeier stability, which is the following. Let me write it like this. Let me write in his notation, and because you now are expert, you will already know what we are talking about. Where this K here is time step. So Randy Levesque uses K for time step, H for delta X. Okay? So if I write this, if I leave the room, if I don't say anything, like half, as we say, I have an expression in Portuguese, right? For an expert, half a word is enough. Sounds strange in English, but we all know in Portuguese what it means. So here, Lax-Richtmeier, it's basically talking about, say, an operator, right? And an operator, as it is evolving in time, what we want is to have this constant, to bounded operator constant, that independs on the discretization. Of course, it depends on the interval we're studying the solution. Okay? Fine. So he mentions this, and then he goes on to the von Neumann analysis that we want to get something a little bit along this scenario, right? That's what with what? With the amplification factor. We go to Fourier. So basically, von Neumann sort of looks for inequalities of this sort using Fourier analysis, which, needless to be said, right? Needless to be said, is for what? Linear constant coefficient PDEs, right? Okay. Then he mentions also briefly, and I will not get, there's a little bit of that in my notes. I'll make some comments, but I'm not going to get into detail, that is like a more, but this is so that you know, more general theory which uses the Kreis matrix theorem. Okay? So usually, you know, in this discussion you will see, and I'm going to come back to this. I really want to come back to this. You will see that when things, so he mentions, when things get sort of, for example, they're not non-constant coefficient or there are other things or whatever, then sometimes you got to reshape your problem and look at matrices, right? And there's pseudo-spectra. There's something that's actually, even Trefetner has, I think he has even a full book on this. I'm not going to get into that in this course. But what I found that he mentions in an interesting way, and he says, okay, let's take a look at the situation with von Neumann. Let's take a situation where we have no boundaries, or we have periodic boundaries with no boundaries, one-dimensional, constant coefficients, okay? And then he mentions a few important things. Before I go into that, before I don't forget, because I think, yeah, let's see if it comes afterwards or not, so that I don't make that mistake and I don't forget. No, I think I should continue this way. So look, things that you already know, but let me mention one thing, is that if we have for example, he gives this example. If we have this this operator here, discrete operator, okay, a central difference, okay, and we do a Fourier analysis of this, so let me skip one point, we can get the following. And let me use his notation so that we also get used to other notations. Let me rewrite this because I'm holding a paper and my handwriting is not good, sorry. So look what happens here. The first thing, some things, I'm sorry, what I'm doing is basically a review because we've seen this. You've done this, right? Even with the Crank-Nicholson homework, there's a little bit of this floating around, but just make sure. I mentioned this to you. So look at this. If I have this discrete derivative, right, and I go to Fourier, right, and we know that derivatives, right, we can write it in matrix form, right? This if I write this as a matrix for all the points on the grid, right? This is a banded matrix. It's actually 0 on the diagonal for this case, right? And the guys and constant guys around it. So Toeplitz matrix. So we can see from here, for example, eigenvalues, right? Or here an eigenvalue of this operator. Oops, I wrote this because his notation was the VW and I. Okay. Just like when we do a derivative, you thinking of a Fourier mode, the derivative of Fourier mode is is actually IK, the Fourier mode. Okay, so in Fourier space, so let me write something here. So something I already mentioned to you, right? In Fourier space, if I do the derivative of f, this is going to be 1 over square root 2 pi minus infinity to infinity. Whoops. Ik e to the ikx f hat k dk. Right? So this is basically, we call it the symbol of the multiplier, right? And if I have here a differential operator, not just one derivative, right? So this, let me write like this, just so it's better. Right? Now if I use L, which is like this, look, AN. And so on, right? Well, we put it like this just to be on the simple side, and so on. This here will be what? A polynomial, right? So I can do this in a very simple way if I go to FFT. But here, the thing is that when we have a different scheme, right, we can write it as a matrix, right? And we know that actually the eigenvalues of the matrix are obtained by using Fourier modes. Okay? So he calls so this is like an eigenvalue, and these guys, just note that this C here is actually the wave number, so it's like I'm doing this. Let me actually change the notation. Right, sorry. So this would be the appropriate notation. And what was I going to say is that, okay, he calls, does he call Eigen? So he puts like this with quote unquote, Levesque puts an Eigen grid function, which would basically be E to to the I xj. Do you see why? Because if I apply this to eta xj, this is what we're doing here, eta xj, we get this guy times the guy. Okay? So this is a little bit how you played, I mentioned too, I think in the Crank-Nicholson problem, to sometimes solve a recurrence relation, depending on how it is, it's useful to use a Fourier mode, right? Okay, now, if another thing that Levesque says, that if you expand this sign here, did I write it right? Yes. If I expand this sign here, I did right. Look, the first order guy is going to be just x, which is hc. This h cancels with this. I just get ixc, which is the exact derivative of the Fourier mode, right? So up to an order, a higher order, right? So approximation. So you see all these things. And then the other thing that he mentions is, okay, now, yes, it's here. So this is going back to this discussion here. Look, we have mentioned that when we do the von Neumann analysis, here it is, von Neumann analysis, we get an amplification factor. Remember, and I said, hey, look, this looks like an amplification factor we had before for ODEs. Okay? But Levesque calls attention, and read this. It's an easy reading. It's organized. It's very good. Which is, it says, okay, so why don't, let's see if you guys can sort of, at first it's not that simple, but as many things I've been saying in the course, after you hear me saying or you read it, say, oh, okay. So why are we doing the von Neumann analysis rather than, for example, using the method of lines? Said like this, I think if it was for me and I was sitting there, it would be a difficult question. But you already have all the information in your head. The thing's linking the information, right? So that's part of the learning process. Look at this. When we did the method, as I presented, and I'll do some exercise, of von Neumann stability, we use Fourier, right? When we use Fourier, we're basically, because the problem is linear, constant, coefficient, so on, we're basically decoupling the modes, right? The modes don't see each other because it's just a linear superposition. Okay? You're with me, right? And then we get an estimate, right, for the amplification factor. That for wave equations, actually, we want the amplification factor. It can be as we saw, it can be slightly greater than 1, so that we get estimates like this, like the Lax-Richtmeier estimate, which has to do with well-posedness and blah, 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 right? But if we're doing a wave equation, we actually want the amplification factor to be 1, right? Just like when we were choosing about the trapezoid rule or the implicit Euler or the explicit Euler, right? For an oscillatory problem, we want it to be on the border of the stability locus because we want it to have absolute value 1, right? Good, so you're with me. But then when we have the amplification factor for the von Neumann condition, we want to quote the amplification factor in a way that it's independent of the k, to some extent, right? It's quoted by something that depends on the time interval or whatever, right? As the estimate. Now, here is the problem. So we get something that's uniform without us having problems, let's say, if k goes to infinity. Sometimes go to by, you're going to see the estimates. We had sometimes 1 plus delta t sine of k blah, blah, blah. Okay? Excuse me. Now, when we do the method of lines, okay, and if we do the method of lines, we transform our PDE into a system of ODEs. Okay? Up to there, fine. It usually gives us an idea. Question you were asking me before the class. Oh, how do I choose a method? Sometimes the first look might be trying to look at things for a small discretization, look at what kind of matrix arises. I don't know, at least that's good also to see the complexity of the method. And the molecule helps you, because the molecule tells you what's the width of the band of the matrix, right? If you have to invert something, if it's an implicit method, blah, blah, blah. But then, if we're going to check convergence through the method of lines and through the eigenvalues of the matrix, you see what I'm getting at? Because, now let me take a step back. If I do the method of lines, I'm doing a semi-discretization. If I'm doing a semi-discretization, I'm transforming my PDE into a system of ODEs, right? And well, we studied ODEs, we know it's easy. You can do and if the system is linear, constant coefficients, this matrix is constant coefficients. Oh, let me look at its eigenvalues. Let me try to put all the eigenvalues, say, inside a disk or something like that. Right? Cool. But, and this is not the discussion, he puts all this into the text, is that the problem is that if I'm trying to do a convergence proof for something, I'm going to let n go to infinity, or n become bigger and bigger. And the matrix becomes bigger and bigger. And the eigenvalues might dash off to infinity, grow more and more and more, which means, well, how do I control all these guys? So the absolute stability associated to the method of lines is complicated, and we're going to get into trouble because if I'm looking for bigger and bigger n's, right? I have no idea. The eigenvalues might be growing and growing. When you go to the von Neumann scenario, you get something which is just, if it's a one equation, it's just a scalar. I'm going to do an example now where it's a multi-step method, so you get a matrix, a 2x2 matrix. But as n goes to infinity, this 2x2 matrix stays as a 2x2 matrix. Because as n goes to infinity, what is growing? It's the k of the Fourier mode, right? Which is bounded from n minus n over 2 to plus n over 2. And if you get a bound that independent of that n, if you get eigenvalues of this matrix, because it's a multi-step method that is bounded independent of the k, that's a much better analysis. You see what I'm saying? Is the story making sense to you, right? Because the method of lines, we're going to get a bigger and bigger matrix, okay? And as we will see, in these examples, some things will sort of, and as you read the text, you will see that some things about these eigenvalues, the multiplicity of the eigenvalues, I'm going to do an example for us, are basically sort of rings a bell, calls our memory for somehow roots of the polynomial that we saw before, and that say, hey, roots of if you have a polynomial that has a root, that's a double root, what do we know about that? The double root cannot have modulus equal to 1. Okay? So I'm going to give you an example that's going to show that. Okay, so that's more or less the blah, 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 my sort of advertisement of Lévesque's very nice book, which I think at this moment of the course, a little bit my notes, as I keep on saying, are not the best organization because I pick from books here and there. I have one day to organize this better. So this book by Lévesque is very good. I recommend you to read this chapter, which is not very big. I mean, you should read as much as you want, and you can, because the book is about our course. Find the difference methods, OZs and PDs. Okay? All right. So let me do, in a sketchy way, I mean, so we don't have to get bored with all the details, a few examples of von Neumann analysis. And the first two are pretty much, I would say, straightforward, besides the calculation. And the third one has a little bit of a subtlety, which makes it important to learn and fun. Okay, so let's go to some examples. Okay, so let's check the stability of upwind, which we already know. One way, and actually this book of Lévesque, he's actually the only book that I know. There's the other book of his where he talks, that I knew for some time, that he talks about what's another thing that I like very much, which is the modified equation, right? How you can sort of get a numerical method, play with the Taylor series, whatever, and cook up another differential equation that better represents the method than the original differential equation. Okay. All right, but now we're going to do it in a different way. Upwind for the wave equation, for the unidirectional wave equation. Okay. Here's the molecule, and here's the method, already with the Fourier, with the current number. Okay, let's do a Fourier analysis. Okay, so this is my grid Fourier mode, and will actually be as he calls, an Eigen grid function. I've got to breathe before I say it because it's a long word, right? Which is a good thing. So it's an Eigen function on the grid. So if we put this in and collect terms, right? So we put substitute in here. Okay, we get oh, my notation's so bad, I don't know why I'm putting the J. Ridiculous. I didn't notice this. Sorry about this. I got to really clean my notes. Sometimes writing too fast. As I'm preparing some years ago. Okay, I don't have an eraser here, but right, there's a J here. Makes no sense to have a J here, right? The J is over here. So this is just like separation of variables, right? The amplitude of the Fourier mode that can vary in time. There's a J here. I think I have an eraser. Let me do this or else I forget, even though it's already scanned. Sorry. I already went this a few times and never noticed. Right? Nobody complained also because it's obvious it's a mistake. But please, if you see something silly, help me clean up my notes. Okay? So basically this is like, if I substitute this in here, I'm getting a discrete ODE in time for the amplitude. Right? So this is basically the sort of the propagator, and then I can write the following. I can write the G. Let me copy so I don't have to do the simple calculations, then do a mistake. So this will give us, right? Because basically, maybe I should have even written it like this. It becomes a little more friendly, simpático, as we say in Portuguese, right? Which is basically the amplification factor for this discrete ODE. Okay? And then, okay, but this guy's complex, right? So I can eventually get this. Let me copy because I don't want to waste time with silly calculations and make a mistake. Okay, so this is really this is our amplification factor, and if you graph this in terms of sigma, and here the amplification factor squared, right? We can see that for sigma equal to 1, this is equal to 1, and for sigma equal to 0, right? It's also equal to 1. These guys, when sigma is equal to 1, these guys kill each other. And then we have something like this, okay? Recall this is negative with negative. So basically, that just confirms what we know, right? That sigma, the Courant number, has to be less or equal to 1 for this guy not to grow, right? And since we have a wave model, we know there's no associated growth in the PDE, okay? Now, the second example, I call this example 1. Second example 2 is this method. Where the molecule is like this, looks like a legitimate method, right? Centered, and so on. Okay? And looks a bit like a mixture of a upwind with a downwind, right? And probably the downwind guy, as you see, will give us a headache. So if we do von Neumann again, just basically Fourier analysis, we will get G, let me skip one step, right, because I don't want to, K delta X, and this will imply that the absolute value is greater than 1, okay, because as you can see, it's going to be this plus this, right? This is imaginary, this squared plus this squared, square root, right? Positive, so it's going to be greater than 1. So the method will indicate for the wave equation, it's going to be growing. There's going to be some instability. And now let me do the other example, which there's something interesting. This method is called leapfrog. Sometimes it has a hyphen here. I don't know. This can write it both ways. So leapfrog, do you know what it means in English? Portuguese has a very... Say it? No, say it. Salto de rana. Yeah, that's literally what it means. In Portuguese, it means frog jumping. Leapfrog would be salto de rana. But actually, if I'm not wrong, this means what we in Portuguese call, I don't know, you're much younger than me. I don't know if you even played this, what I played when I was a kid. I mean, played, did it a few times, and it was called carniça. Would you know what carniça is? Saltar carniça? You know, Lucas, you know? Huh? What is it? No, carniça can mean also like rotten meat and so on, right? But there's a kid's sort of little game called carniça. Do you remember, Lucas? Yeah, you guys are too young, much younger than me. I'm old enough to be for sure your father, maybe almost your grandfather. But don't laugh. Respect for the teacher, respect. But carniça is a game which I think in the US is also called leapfrog, which you stay like this, right? It's a little bit like Olympic gymnastics. You come running and you put your hands here on the back of your friend and you open your legs and you jump over, right? So it's called, I think that's in English, it's called leapfrog. So it's basically you're skipping over something and here's the molecule. Let me write the method. Where is it? The method is like this. Okay, so here's the molecule, right? There's no JN guy. That's why I have this atom in blank. Okay? So it's a 3-level method because it's using n minus 1 and n plus 1. Okay? And it's going to be sort of centered, right? Centered in time, centered in space. Okay? So see, in space, it is centered here. Oh, in here it's wrong, sorry. I saw some of you looking strange. Maybe that wasn't a mistake, right? And here it's centered in time. Okay, so this method, because it's sometimes things when are centered, usually you gain orders, right? You kill terms because there's sort of the symmetry and so on. So this method is second order. And let's see its property, okay? So let's do a von Neumann analysis of the leapfrog. Which is basically a Fourier analysis. Okay, and we get right. I'm not plug in and do the calculation with this so we get this. I hope I copied right. Okay. So this is our Fourier analysis. And let me show you basically in 2 different ways that this can be done. So this leads, right? So this leads, so we have, excuse me. So we have this, which means no, let me write the different. Let me keep actually the notation of my notes that I decided to use, which is r squared. So let me leave it like this and see if you follow what I'm doing, or in some places, this notation of this guy, when you have systems or you have, right, when things become, this becomes the amplification matrix, sometimes called. So can you see what I did? Right? So I'm doing the same thing in 2 different flavors. Okay? So let me go over this, just make sure, I can see maybe some of you already know what I'm doing, but just communicate well. So I wrote this, right? Where? Here? Oh, yeah, this one is -1. Thank you. Good that that's when the age difference is very good, right? You might not know some games I played as a child, but you're much faster picking up the mistakes. So that's good. All right. So You see, very good. So we have two things here. Over there on that board, we did things in two different flavors, but just it's good as an exercise, as a simple exercise. We have this recurrence relation, right? This is basically our discrete ODE for the amplitude of the Fourier mode. That's the fancy way of saying it. Agree? Right? ODE, discrete ODE for the amplitude of the respective Fourier mode, which is a generic one, right? Okay, now this is also, right, this looks like I've crossed it. This is also a recurrence relation. And we know how to solve recurrence relations. We find the roots, right? So this gives us the roots of recurrence relation, okay? But also I find it interesting, because I'm going to just mention very briefly, I find it interesting also, hey, just like when we have, say, second order, when we have a second order ODE or whatever, we can transform it into a system, right? By saying, okay, one guy is just a derivative of the other one, you call it that one variable, blah, blah, blah. So I'm doing basically here, to some extent, the same thing, to some extent, right? So I transform this recurrence relation, which has two roots, right, into a system, sort of like it would be a first order system, right? This would be like a second order equation, and now this looks like a first order, this is just a notation. This is my first order system, okay? And the roots of this guy, right, are basically the eigenvalues of this matrix, right? The characteristic polynomial and so on. So let's write the roots. Let me call it lambda. The note is called lambda. So we have lambda, so either roots or eigenvalues, lambda plus or minus, is equal to plus or minus, let me write it like this, 1 minus sigma squared plus I okay. So these are the roots. And we can conclude, right? So my notes are a little messy here, and they were, I forget now if this part I actually scanned, if you find it in the notes or not, let me know, okay? Because there's one thing, it might be scanned, and you already have it, so I didn't forget to scan it, which would be good if I didn't forget to scan it. But there's typos, which means it would be good if I have forgot to scan it, because then I think there's some signs here that were wrong. The result at the end is correct, but there are missing signs, okay? Plus or minus signs that were switched. So let me know if you see these parts here in the notes afterwards. I can check it, but if I forget, let me know, okay, if you have this or not. Okay, so here we have the following. So if sigma is less or equal to 1, is this stable? That's a question. Just like, right? Just like we had for the other problem. For this one, right? If we had less or equal to 1, we were okay for the wave equation. Here we're doing the wave equation also. Well, let's think of this. There's a subtlety here, right? That I wouldn't at first have had picked up it. So let's do okay. For sigma less than 1, it is stable. Okay? So you can check and see that for sigma less than 1, it is stable. Say it, Marcel.
But lambda is not always 1.
Lambda
Is always 1.
and maybe, and I'm missing here something. Yes, you're right. Yeah, very good point. Very good point. See, it's good to have young people in the crowd, right? No, but very good point, because this guy squared plus this guy squared, this guy kills this, it's always 1. Very good point. Excellent. Even helped. I was going to mention, I was forgetting to mention that. Very good. Now, okay. Now look at this. Very good. Okay, very good. So what happens now, so let me ask you the following question. Let me ask you then the following question. What happens for sigma equal to 1? Wait, I'm doing something. Wait a second. What am I doing here? I think I still have a mistake somewhere. I think I still have a mistake somewhere. Oh no, I think I got it. Let's see. So, say it again, Lucas. Não, fala em português. Onde está? Very good. It depends where my k delta x is. So the thing is, I have to check, but I think here's the thing. You want to say something? Pode falar. You can speak. You can speak. You think what should be plus inside? No, here it's here you think it's plus? No, here's minus.
I mean, minus 1 plus sigma squared. Or maybe an I think.
I don't know. Let's double check. So it's a little bit of an exercise for all of us to double check this, because I found some typos, maybe I didn't fix them all. But here's the thing. So here's the thing. What happens for sigma equals to 1? We have double roots. Okay? So we get double roots. And when we get double roots, what happens? If you want to write the solution, right? So remember that if we have double roots, it's like having, like this. Remember that when we had a recurrence relation and we had double roots, we would have something like this. So we would have a slow growth in time. Okay? So that means, I have some mistake maybe somewhere, I'll check this, slow growth in time. So that means that it's always good to use it slightly below 1 so that you avoid this. And as you said, and as Lucas said, Lucas said, this is, the double roots happens with kx. I'm forgetting to put the information, kx equal to pi over 2. So let me check. I have it here in the notes. So it's for a special kx, as Lucas just said, where this is going to be, this is going to be minus -1. Oh, here it is, yeah, sure. Now I see it, no. Because if this is, if sigma is 1 and this is also 1, it kills this guy, right? That's why. So I don't think there's mistakes, but anyway, right? Okay? So as you said, correctly. Now tell me, where did your intuition tell you in the beginning that for a specific kx, you said something about a specific kx. How did that come to you?
Eu calculei módulo para ver onde é que era maior que 1 e onde que era menor.
For these guys?
Yeah.
Okay. So that you were checking the modulus where it was bigger, the sign was bigger than 1 or equal, at maximum equal to 1, right? Okay, very good. So that's very good. So you see, I was getting confused. So it's actually for this mode, which is mode k over 2 delta x, we know that the interval is from minus to plus pi over delta x, right? But there in the middle, there is a mode that could slowly grow if I used sigma equal to 1, right? And therefore, it's safer also to put it slightly less than 1 so that you avoid this, okay? With leapfrog. Okay, so thank you for helping me. And yeah, so I have some, but it's incomplete. It's not very good, and it's more well done. It's more well done, I think, now that I mentioned the reference of Levesque's book. In my notes, it's not very well done, but let me write one comment here. Note when so now let's take just a quick comment to see what happens. I'm skipping a little things related to the Christ method, which is I try to do a summary here. It's not very good. Now that you have this text, it's much better done. And I'm not going to cover it. I'm going to move on to something soon. But let me make one comment which I think is important. When the matrix is defective, what happens when the matrix is defective? Here we saw double roots, right? Which would mean double eigenvalues, right? It could be diagonalized, but let's think of the following. A is M, J, where J is the Jordan form, okay? And let's suppose that we have a Jordan block, Ji. Okay, if I have a Jordan block like this. Okay. So we need care because, say, if a Jordan block appears in our analysis, because J to the n So it's going to have this structure. Okay, so if we have, so we have to be careful. It's like here we had the double roots, so we had a slow growth. If we have then something like a Jordan block, okay, so an eigenvalue with a different multiplicity, right, in terms of the algebraic multiplicity and the geometric multiplicity, and having a full range of eigenvectors, right? So then, this guy, as we take the power of this block, this is what's going to happen. And this is basically, for us, a growth in time. Okay? So these are some of the comments that will arise when, say, one is looking, among other things, when is looking at the Christ matrix analysis, which, as I mentioned, sometimes it's more difficult, it's more complicated, but if you don't have constant coefficients or whatever, you have to go to a matrix formulation. Okay? So this is just to point out to more sophisticated things, which I will not mention here. So, okay, I have a few minutes. I wasn't quite sure if I was going to get there. And I want to talk about start talking a little bit about boundary value problems. Right, and eventually we're going to talk about Laplace's equation, which is a boundary value problem. But let me talk about one with ODEs. So let me, as a review for us to refresh our memories, it may be, I would guess, I'm going to ask you a question. I would guess that you have heard of what I'm going to talk about. But if you haven't heard, the better. If you had heard, it's a refreshing. Who of you have heard of the shooting method? Know what I'm talking about, the shooting method. It's for ODEs, boundary value ODEs, which actually I'm not 100% sure how it is translated in Portuguese. Shooting is shooting, and Portuguese, because it also sounds similar, I've used it in Portuguese. I've seen people say in Portugal, método do chute, right? Because it's like trying to kick on a target. But have you heard about it? Do you know what I'm talking about? And how did you heard it? No, how? What was the name you heard for it?
Shooting.
In Portuguese, shooting. Yeah, I've seen people in Portuguese also using the Anglicism, right? Using the word in English, shooting method. Okay, so here's the shooting method, okay? So good for us to so this is a boundary value problem. Okay, and let's take this problem, which are typical problems that appears in, say, Sturm-Liouville type of problems. Okay, so these are, let me put here, so hypotheses. And that, before I forget, also let me put, this I'm using actually the more introductory book by Burden and Ferris. So these guys are continuous in AB. Q of x is greater than 0, in AB, which is conditions that, right, guarantee unique solutions on. A more advanced book, there's a more advanced but well-known, which is a book by Herb Keller, okay, which is Siam 1960. 76, I think. I think it's even older. Maybe it's a reprint. So Herb Keller. There's actually two famous mathematicians that I know called Keller, and they're brothers. One is Joe Keller, which was actually my academic grandfather. He was the advisor of my advisor. And there's Herb Keller, his brother, who's a numerical analyst and was professor at Caltech. Okay, so how's the shooting method? So let me ask you. We have a little bit of minutes. We'll see. Yeah, let's see how far I go. At least let me warm up this problem for next class. I'm sure I'm not going to finish everything. So how would you solve this problem? It's an OD, right? That you have to satisfy the conditions here and here. Okay, so we put the grid inside. This is X. How do I guarantee that I'll be correct here and be correct there? So there's for sure there's a sort of a non-local aspect, right? You got to make sure you satisfy these two values. You could maybe discretize. One way is maybe discretize. We'll write maybe a matrix. Try to put define some derivatives for these guys and make a matrix. Try to solve for this, whatever. But there's the shooting method. In the shooting method, I think it's some of the, those ideas, right? People are smart. There are very smart people out there, and some very clever ideas and transforming problems, right? Mathematicians about that, transforming to something I know how to solve. So the trick of the shooting problem is to transform this boundary value problem into an initial value problem, which is exactly what we've been seeing up to now. Okay? So this problem, since it's linear, somebody found this very nice trick. Look at this trick. And probably, let's see, I'll probably finish at that so we can start at a good point next class. But it'll be close. So we have I'm writing in Portuguese here, sorry. Initial value problem A is, so let me call this, so I don't have to repeat, star 1. Okay, star 1 is the differential equation. So we have star 1 with this condition here. This initial condition here, and initial value problem B is star 2 with this initial value problem here. Okay? So this is a motivation. It's not yet the shooting problem. This is a motivation for the shooting problem. So due to linearity, gives us that y of x is going to be equal to y1 of x plus beta minus y1 of b divided by y2 of b, y2 of x. Okay? So you can check this. So is this a surprise? Well, it's nice, but it's not so much of a surprise, right? Why is not so much of a surprise that I can do this trick? It's not yet the shooting method. It just shows that for the linear problem, it's very simple. Why can I do this? Look at this. Why am I highlighting these two guys? Because these are two linearly independent initial conditions, right? How many degrees of freedom I have here? 2. This is a dynamical system. If I think of x as time, but it's not really, if I think of x as time, it's like I'm saying I want to leave here, I'm going to do an orbit, and I have to make sure I'm going to land here, right? If I thought of something. And that's the spirit of the shooting method. I'm going to start leave here, but look, I cannot miss this target. That's why it's the shooting method. Well, if we start with the linear problem, then the intuition is, hey, this is a 2-dimensional problem. I have 2 degrees of freedom. I could maybe write the fundamental matrix, or write the general solution, which is 2 homogeneous solutions. So this is basically what these guys give me, and these are the constants. The constant for this one is 1, and the constant for the second solution is this. Let's check. If x is equal to alpha, right? If x is equal, not alpha, to a, right? If x is equal to a, this is alpha. This is y2 of a, and y2 of a is 0. Boof, okay? And if x is equal to beta, then b, sorry, say alpha. Okay, a is equal to alpha. If x is equal to b, this guy cancels this guy cancels this guy, and it's beta. So it's satisfied boundary conditions. Okay, very cool. But if the problem is nonlinear, let me finish the class here for next class. If now we look at this nonlinear problem, we cannot use these tricks. Because this is nonlinear. I cannot use superposition. Okay? So this was just to show that, okay, this was kind of nice. So then the idea is going to, and we'll see next class, is still to think of initial value problems, okay, and do this. We're always going to start, this is B, this is beta. We're always going to start from here as an initial condition, okay, and because this problem has an initial condition, and I want to do an initial value problem, so I'm going to do y2 prime equals to f, ya is equal to alpha, and y prime a is equal to something, which this means I'm starting here, and this is the slope, exactly the angle at which I'm going to shoot. And we're going to construct one then will suggest, by the shooting method, an iterative scheme where you shoot, you miss the target, but you learn, you change the angle again, and eventually you might converge to here. So that's the iterative shooting method. Next class. Okay? So this is just to show the first one was a little one, just so, hey, you don't even have to, there's no big deal. How do I solve it? I just, solve it for those 2 initial values, right? I mean, I forgot to say, right? For this one, I went a little too fast. How do I solve this? Solve these 2 initial value problems with whatever you want, glue them together, we're done, right? You still got to solve it numerically. Now, when it's nonlinear, this trick doesn't work. But then you can build an iterative scheme where it's okay to miss the target, but you learn from each time you miss the target, and you improve your second shot. Nice, right? So we'll see this on Monday.